Ever get that feeling where you're like, wow, my computer's doing like a million things at once?
Yeah.
Like, how does it even...
Right.
Right. Well, today's deep dive, we're going deep into operating systems.
Okay.
Specifically, we're looking at how they're handling multiple processes at the same time.
Right.
Without everything, exploding.
Yeah.
Which is what it feels like should happen.
It's a lot.
It's a lot. And the thing is, we're working from some pretty technical documentation, which is always fun.
Sure.
But the interesting thing I'm finding is how relatable it actually is.
Okay.
Like in terms of how these systems kind of manage conflict.
Interesting.
So it's pretty cool. So the excerpt kind of dives right into this concept of concurrency. And we're talking about multiple processes basically happening, not necessarily at the exact same time, but like in overlapping time frames.
Okay.
So like when you have a million tabs open on your web browser,
Right.
that's kind of what we're talking about.
Got it.
And that's actually different, I learned, from parallelism,
Right.
which is true simultaneous execution.
Okay.
So that would be like if you have multiple processors and they're each running a completely separate task.
Okay, that makes sense.
So this is more like the juggling act.
Got it.
Where things are happening kind of all at once.
Right.
And where things get really interesting is when these processes need to share resources.
Okay.
Right? Because if you think about it, it's like, two cooks trying to use the same stovetop at the same time.
Yeah, it's a recipe for disaster.
It's chaos. Right. And so that's where this whole idea of critical sections comes in, which the source material kind of introduces.
Mm-hmm.
And essentially, it's like, how do you create a system where only one cook can access the stove at a time?
Right. Because you need to make sure that, one person's dish isn't getting, messed up because someone else is trying to use the same pan or something like that.
Exactly.
It's about, preventing that data corruption. You can think about it that way. Like if two processes are trying to modify, let's say, shared data at the same time,
right,
you could end up with a jumbled mess.
You're gibberish.
Exactly. Critical sections, they essentially make sure that when one process is, let's say, working with that shared data, others are kind of locked out. And that just ensures that everything stays, consistent and accurate.
Okay, so it's like a system of like locks on a shared resource.
Exactly, yeah.
Okay, that makes sense.
Yeah.
But then the excerpt, it's like it lays down the law. It gives us these 4 requirements that any system for managing these critical sections has to meet. And I'm just gonna lift them out here because it's quite something. Mutual exclusion, lockout prevention, starvation prevention, and deadlock prevention.
I feel like we're talking about
like fairness and order in the digital world.
Absolutely. And mutual exclusion, that's that fundamental rule, right? Like only one process can be in that critical section at a time. But, it's not enough to just, have that one rule. You have to think about all the other things that could go wrong. So that's where these other things come in. So lockout prevention, that makes sure that a process that isn't even interested in the critical section, it doesn't accidentally prevent others from getting in. So, it's like if you have, I don't know, let's say a coffee machine, right? And someone who doesn't even want coffee is standing in front of it.
Right.
Blocking everyone else from getting their caffeine fix.
Okay, yeah, so 2 down, 2 to go. What about starvation and deadlock? Those sound intense.
They do. So starvation prevention, that makes sure that a process doesn't keep getting denied access to the critical section just because others are always getting there first.
Oh.
So it's like, if you're always at the back of the line,
Right.
you're never going to get your turn. And then deadlock prevention, that's all about avoiding those situations where 2 processes are essentially stuck because each one is waiting for the other to release a resource.
Oh, okay.
So that's like, if you're trying to walk through a doorway at the same time, someone's got to yield.
Right. Someone's got to back up.
Exactly.
Okay, that makes a lot of sense.
Yeah.
But I'm curious, like, how do operating systems actually put these rules into action? Because, we're talking about lines of code, right?
Right.
How do they enforce these rules?
Yeah, it's pretty amazing when you think about it. So the excerpt actually gives this example of a will wait variable.
Okay.
And it seems kind of simple, right? But it's actually pretty clever.
Okay.
It's like a flag that a process can set to basically say, hey, I want to enter this critical section.
Okay.
And by just checking this flag, the operating system can manage access and ensure that, not everyone's trying to barge in at the same time.
So like a simple raise your hand if you have a question kind of system.
Exactly, yeah. And this simple mechanism, it kind of hints at, bigger concepts like semaphores and mutexes, which are more, let's say, sophisticated tools that are used in this whole world of concurrency control. But it all starts with that simple idea.
That's wild. It's like this elegant little solution for what could be a huge mess.
Yeah.
And it's cool that they highlight that. But the thing is, it's not all just competition.
Right.
Like, our excerpt doesn't just focus on that. It also talks about how processes have to cooperate.
Yeah, absolutely. And that's where we get into the, classic producer-consumer problem, which is a great example of this.
Okay, so break it down for me. What is the producer-consumer problem?
Okay, so imagine, like, a factory production line, right?
Okay.
You've got one process, the producer, that's creating these items, whatever they may be, and adding them to a buffer. Think of it like a storage area.
Okay.
And then you've got another process, the consumer, that's taking those items from the buffer and actually using them.
Okay. So it's like a carefully choreographed dance between these two processes.
Exactly. And it's crucial that they don't step on each other's toes. For instance, the producer can't just keep adding items if the buffer's full.
Right, overflowing.
Exactly.
Yeah.
And the consumer can't take items if it's empty.
Right.
So they need a way to, communicate, to synchronize their actions.
Okay.
And this ensures that there's this smooth flow of data without, anything getting overwritten or lost in the process.
So they're like passing the baton, but they have to do it at the right time.
Exactly, a perfectly timed handoff. And this, this might seem like a very specific example, but it's actually crucial in real-world programming.
Really?
Oh, yeah. It pops up everywhere, from applications that use multiple threads to client-server interactions. It's a fundamental concept.
It's kind of mind-blowing when you think about it. Like, all this is happening behind the scenes every time we use our computers. This whole hidden world of processes constantly talking, coordinating, and it's all thanks to these elegant rules of operating systems.
It really makes you appreciate how much complexity there is, even in seemingly simple interactions, right?
Absolutely.
And, the challenges of managing processes in a computer, they actually mirror the challenges we face in our own lives. Think about coordinating tasks, managing resources, even collaborating with others. We need those same principles of, clear communication, understanding dependencies, and make sure everyone's on the same page to avoid utter chaos.
Wow, so the next time my computer seems to be working miracles, I'll remember it's not magic. It's this elegant dance of concurrency control. It's honestly a testament to the ingenuity of, computer science, and it's a fascinating reflection of, like you said, the complexities that we navigate every single day.
Well said.
Well, on that note, I think we've done our deep dive for today.
I think so.
Until next time.
Ever get that feeling when your computer's running a million things at once and you just know it's about to keel over? Well, today's deep dive is all about how operating systems wrangle that digital chaos.
All right.
Using a surprisingly simple tool, the mutex lock.
Right.
You actually sent us some notes on this, and let me tell you, they got the gears turning.
What's so fascinating about mutex locks is that they're elegant in their simplicity.
Okay.
We're talking about preventing digital mayhem with essentially a single switch.
Wow.
But the implications of that switch, they're everywhere in modern computing.
Okay, so let's unpack this digital mayhem bit first.
Sure.
Imagine a kitchen, right? But instead of one organized chef, there's a whole crowd trying to use the same pan at the exact same time.
You'd have a recipe for disaster. Spaghetti flying, sauces splattering, utter chaos. Now replace that pan with something like a chunk of computer memory.
Okay.
Or a file being accessed by multiple processes at once. That, my friend, is the crux of the problem that mutex locks solve.
So are you saying my computer is basically a chaotic kitchen during rush hour?
In a way, yes.
Yeah.
And those moments when everything wants to access the same resource at the same time,
Yeah.
that's what we call a critical section, a recipe for errors and crashes if we're not careful.
Got it. Critical section equals potential meltdown.
Exactly.
Enter the trusty mutex lock, our digital bouncer, here to maintain order.
Exactly. Think of it as a very exclusive club. The mutex lock stands at the door and makes sure only one process gets into that critical section at a time.
Okay.
This way, everyone gets what they need without stepping on each other's toes.
Okay, that makes sense. But how does this bouncer actually work? Is there a tiny clipboard with a lead of processes waiting to get in?
Even simpler than that. Remember that single switch idea I mentioned?
Yeah.
That's where the magic happens. A mutex lock uses a Boolean variable, a simple on-off switch. Lock available. 1, meaning yes. Lock busy. 0, meaning not a chance.
So it's like a digital occupied sign for that critical section.
Exactly.
Simple yet effective.
Exactly. And when a process wants access to the critical section, it tries to acquire the lock. If the lock is free, meaning the Boolean variable is set to 1, the process gets the green light to proceed.
So the process waltzes into the critical section, does its thing, and then what? Does it just leave the door swinging open for the next process?
Not at all. Remember, this system is all about order. Once a process is finished with the critical section, it releases the lock,
Okay.
flipping that Boolean variable back to 0, or vacant, if you will.
Ah, so it's like checking out of a hotel room.
Yes.
You got to let the front desk know you're done so they can give the room to the next eager guest.
Precisely. And this acquire and release dance is absolutely crucial
Okay.
for preventing those digital kitchen nightmares we were talking about. The entire system relies on these two actions happening in a precise, uninterruptible sequence.
Uninterruptible, like a perfectly executed dance move.
Exactly. And that's where the concept of atomicity comes in. These operations, acquiring and releasing the lock, need to happen as if they were a single indivisible step.
Gotcha.
No room for any awkward missteps or interruptions.
Because even a tiny interruption could send the whole carefully orchestrated system into a tailspin, right?
Precisely. Now imagine for a moment that you've got a whole line of processes all waiting their turn for the mutex lock.
Okay.
This, my friend, is where things can get a little sticky.
Oh, I'm sensing another analogy coming on. Lay it on me.
Picture this. You're that process stuck in a holding pattern,
Okay.
repeatedly checking if the lock is free.
Yeah.
Round and round you go, consuming precious processing power without actually accomplishing anything. We call this busy waiting, and it's not exactly the most efficient use of resources. It's like hitting the refresh button on your browser over and over, hoping that concert ticket will magically become available.
Talk about frustrating. And I bet this kind of spinning your wheels can really bog down the whole system, can it?
Absolutely. It's like a digital traffic jam, with everyone vying for the same parking spot.
Oh, no.
This is where the operating system steps in with a clever trick called context switching.
Okay.
Instead of letting a process hog the CPU while it's stuck in a busy waiting loop, the OS can temporarily switch it out,
Okay.
giving another process a chance to run. Think of it as the operating system playing traffic cop, directing processes and preventing gridlock.
So it's a bit like saying, hey, instead of burning gas idling here, why don't you pull over for a bit, let some other cars through, and we'll give you a heads up when the mutex lock is free.
A very apt analogy. It's all about maximizing efficiency and ensuring that everyone gets their fair share of CPU time.
Makes sense.
And this, my friend, is where the debate between different types of mutex locks, specifically spin locks, comes into play.
Spin locks. Okay, now you've piqued my curiosity. What makes them different from the regular mutex locks we've been discussing?
Well, spin locks are like the impatient drivers in our traffic analogy. They'd rather keep circling the block, hoping for that parking spot to open up, than pull over and wait their turn.
Oh, okay.
In other words, spin locks keep the CPU busy, repeatedly checking the lock status, instead of yielding to the operating system for context switching.
Okay.
You see, context switching, while efficient in many cases, does come with a small overhead.
Right.
A bit like the time it takes to parallel park.
So in some situations, it might actually be faster to just spin for a little bit, hoping the lock becomes available quickly.
Exactly. If the time it takes to release the lock is shorter than the time it takes to perform 2 context switches, then a spin lock can actually be the more performant option. It's all about choosing the right tool for the job.
So it's like weighing the pros and cons of parking strategies in a busy city.
Right.
Sometimes a little patience in context switching is the way to go,
Yeah,
but other times a bit of aggressive circling or spinning pays off.
precisely. And that's what makes this whole field so fascinating. It's about understanding the nuances of these tools, the trade-offs involved,
Right.
and when to apply which technique for optimal performance.
It's all about working smarter, not harder, even at the level of individual processes.
Exactly. Now, let's bring this all back to your digital life. You've probably experienced mutex locks in action without even realizing it. Remember that time you snagged the last ticket to a sold-out concert online?
Oh yeah, the feeling of triumph when you finally get through the checkout process.
Well, behind the scenes, mutex locks were working overtime to ensure that only one person could purchase that ticket at a time. They're the unsung heroes of smooth online transactions, preventing double bookings and keeping the digital peace.
That's amazing. So mutex locks are like the invisible force ensuring fairness
Yes.
and order in the chaotic world of online ticketing.
Exactly. And it's not just ticket booking. Think about database transactions, where you absolutely need to make sure that data is updated consistently.
Right.
Or managing access to shared resources like printers in a network.
Okay.
Mutex locks are everywhere, quietly keeping our digital lives running smoothly.
It's incredible how such a simple concept can have such a profound impact on the way our computers and even our online experiences function.
It really is. And the beauty of it is that we've only just scratched the surface here. There's a whole universe of concurrency tools and techniques out there. Semaphores, condition variables, monitors, each with its own strengths and use cases.
So this deep dive has actually opened the door to a whole new world of exploration for me.
And that's the beauty of it all. We've given you a taste of how operating systems use mutex locks to orchestrate the incredible dance of concurrency.
Right.
But there's always more to discover. Keep that curiosity alive, keep asking those what-if questions, and you'll continue to uncover the hidden wonders of the digital world.
Words to live by. Well, on that note, a huge thank you to you for joining us on this deep dive into the world of mutex locks. You've given us a newfound appreciation for the elegant solutions that keep our digital lives from descending into chaos.
The pleasure was all mine. Until next time.
Welcome to the deep dive. We're going to untangle how computers juggle tons of tasks without causing a digital meltdown.
It's a bit like orchestrating a symphony, right? Each instrument, or in our case, each process, needs to play its part at the right time.
And that's where semaphores come in our topic for today. I've got some pretty techie excerpts here. Listeners sent them in, so buckle up. We're about to see how these semaphores keep everything in sync.
It's a bit more exciting than a signal flag at sea, that's for sure. These excerpts really get into the weeds of how operating systems prevent processes from tripping over each other.
The excerpts I've got here mention something called CS problems.
CS problems, short for computer science problems. Basically, imagine a bunch of cooks trying to share the same kitchen at the same time. One's chopping veggies, another's at the stove chaos, right?
Yeah, a recipe for disaster.
Exactly. And the excerpts go into how trying to solve these concurrency issues, as we call these situations, with just software. It's like trying to direct traffic with just your hands. It might work at a small intersection, but imagine rush hour in a busy city. Complete pandemonium.
So basic software solutions, they're kind of like using duct tape to fix a leaky pipe. It might work for a little bit. So these semaphores, this more systematic solution as they're called, how do they actually work?
Think of a semaphore like a bouncer at a club. The club is the critical section, the shared resource, like our stovetop from earlier. The semaphore, with its value, determines how many processes can enter that critical section at any given time.
Okay, so it's like a control mechanism. So instead of programs constantly asking, hey, is it free yet? Is it free yet? They have to go through the bouncer, the semaphore.
Exactly. The excerpts call these P and V operations. Think of them as the semaphore's language. A process does a P operation to ask, can I in? The semaphore checks if it can let another process in, and then either lets the process through or makes it wait.
So the semaphore is always in control, and the V operation is?
V is basically the process saying, okay, I'm done, you can let someone else in. The semaphore updates its count, and then maybe lets another waiting process in.
Elegant, right. No more digital food fights. The excerpts mention that this works for any number of processes, not just two, like some simpler solutions try to handle.
Absolutely, and that's key. Because think about how many processes are running on your computer right now. Hundreds, if not thousands, all potentially needing access to the same resources.
And speaking of resources, the material you sent over mentioned something called the bounded buffer problem. What's that all about?
Ah, yes, the bounded buffer problem. Imagine a conveyor belt, right? But this conveyor belt is like a buffer. It's only got so much space. Now you've got one process, the producer putting things on the belt, and another, the consumer, taking them off.
Sounds like a well-choreographed dance.
It should be, but without semaphores, it's a recipe for disaster. The producer might try to overload the belt, or the consumer might try to take something off when it's empty.
And that's where our trusty semaphore friends swoop in to save the day. How do they do it?
The excerpts explain we use two semaphores. One semaphore keeps track of the empty slots on the conveyor belt, and the other keeps track of the filled slots. So before the producer can put something on, it has to check with the empty slots semaphore. And before the consumer can take something off, it needs to check with the filled slots semaphore.
Brilliant. A simple but powerful concept, wouldn't you say?
Absolutely. It's a testament to how elegant solutions can solve complex problems.
Something that stood out to me in these excerpts was how mutex and semaphore were practically used interchangeably.
Right, and while they're both synchronization tools, there's a subtle difference. Think of a mutex as a key to a single lock. Only one person can hold the key and access whatever's locked at any given time.
And a semaphore.
A semaphore is like having multiple copies of the key. You can control how many people have access to that locked resource simultaneously.
That's a great way to put it.
They both have their uses, but understanding the distinction is key to choosing the right tool for the job.
Well said. So, to wrap things up, from managing databases to ensuring smooth communication between your apps, semaphores are quietly working behind the scenes, making sure our digital lives run without a hitch.
And it all comes back to that elegant dance of P&V, managing access to shared resources. Fascinating stuff.
It really is. Think about it, listeners. Every time you stream a video, play a game, or even just open a document, chances are semaphores are working their magic to keep things running smoothly. And with that, we come to the end of another deep dive. Until next time.
Ever feel like your computer's juggling a million things at once?
It really is.
It's kind of wild when you stop and think about it. Like
Yeah.
right now, I've got a bunch of stuff running in the background, but it's all good. It's all working.
Right.
So today's deep dive, we're going right to the heart of how computers manage to do this whole multitasking thing without causing total system meltdown. We're talking about concurrency control and, more specifically, a little something called semaphores.
That's right.
Semaphores.
Yeah, they're kind of like the unsung heroes, you know,
Yeah?
your operating system.
Okay, so before we get into the nitty-gritty, can you just give us a quick, what are semaphores and why should we care?
Basically, you can think of a semaphore like a traffic signal. They're there to make sure that different processes, which are basically the individual tasks that your computer's handling,
Right.
those processes, they need to access shared resources.
Like memory, files.
Exactly. All that stuff, and without some way to coordinate that access, things could get messy.
Yeah. It'd be like a digital freeway with no rules.
Exactly.
Everyone just crashing into each other.
Total chaos.
So semaphores are like, hey, wait, your turn.
Precisely.
Don't want to push that analogy too far, but I get it.
Right.
So is there actually something in a computer's hardware itself that helps with this whole semaphore thing? Or is it all software?
Oh, no. The hardware's got its part to play for sure.
Yeah.
Modern computers, they have special instructions built right in just for this kind of synchronization. One of the big ones you'll hear about is the test and set instructions. Test and set.
Yeah, or TS for short.
Yeah.
You can think of it like, imagine trying to grab a token really fast.
Okay.
And if you're the first one to grab it,
You win.
you get to use whatever resource it's protected.
You get to go, but if
Yeah.
you don't, you got to try again later.
Exactly. You got to try again later. So it's very fast. It's very exclusive. And that's kind of the foundation for how semaphores work at a hardware level.
That's really interesting, but it also seems like it could lead to a lot of processes constantly trying and failing to grab that token, you know?
Yeah.
Is that a problem? It could be. I mean, imagine a whole bunch of processes all trying to access the same resource at the same time. That's where the design of the semaphore really comes in. So it takes these basic hardware instructions, this TS instruction, for example, and it builds on them to create more sophisticated control mechanisms.
So tell me about these mechanisms then. What are the different types of semaphores?
So the simplest kind of semaphore, you've got the binary semaphore. You can think of it like an on-off switch.
Okay.
It's either a 1 or a 0, resource available, not available. And these are implemented directly using that TS instruction we talked about earlier. But
Yeah.
sometimes you need a little bit more control than just a simple on or off.
Yeah, makes sense. Like what if you have multiple parking spaces, not just one?
That is a fantastic analogy because that's
Yeah.
exactly where general semaphores come in.
Okay.
And yeah, you can think of it like that. So instead of just one space, you've got a whole parking lot. And the semaphore keeps track of how many spaces are free. So if you've got, say, 5 spaces,
Right.
the semaphore allows 5 cars in, no problem. But once those spaces are full, any other cars trying to enter, well, they've got to wait until a spot opens up.
Okay, I'm really liking this parking garage analogy.
Yeah.
So if we stick with that, how does a process actually enter and exit this controlled space? What's the actual mechanism?
So this is where those famous P and V operations come in.
P and V?
Yeah, P stands for, well, it's actually from the Dutch word proberen, which means to test.
Okay.
But for our purposes, think of it as try to park.
Try to park. I love it.
Okay.
So what happens?
So if there is a space free, if that semaphore counter is greater than 0, the process gets the green light, goes on in, and that counter, it decrements by 1 to show that a space has been taken.
Okay, so P is like taking a ticket to enter a museum, right?
Yeah.
Once you're in, there's one less ticket available.
Okay.
What about V? What's that about?
So V, that's short for verhogen, which means to increment. Basically, it's signaling that you're leaving the garage, you're freeing up a space. So V increments the semaphore counter, lets another process know that it can P its way in.
This is really quite elegant when you break it down like this. It's like a perfectly synchronized dance of processes, all thanks to these simple little operations. But I'm also kind of cringing a little bit thinking about what it must have been like before semaphores were a thing. Like what kind of craziness would happen without them.
Oh man, imagine you're trying to book a flight online. You found the perfect flight, perfect itinerary, you've put all your information in, and you're just about to click confirm purchase.
Uh-oh.
But in the background, without semaphores, another process might be trying to sell that exact same seat to somebody else at the same time. And then boom, data corruption, you've got double bookings, it'd be a nightmare.
That's a disaster.
So semaphores are there to prevent that kind of chaos, making sure that transactions like this happen in the right order, one after the other, and that the data stays consistent.
Wow, so semaphores are basically essential for everything on our computers then, huh?
Pretty much. I mean, they're fundamental for operating systems, databases, you name it. Anywhere where you've got these concurrent processes that need to work together and share resources, semaphores are there behind the scenes, saving us from all sorts of potential headaches.
Semaphores. The tiny traffic cops of the digital world. It's kind of amazing how something most of us don't even know exists plays such a crucial role in our digital lives.
Yeah, it really is. It makes you appreciate the elegance of some of these solutions that, we just take for granted every day.
Totally. But you did say most of us a minute ago. Are there people who actually do need to think about semaphores regularly?
Oh, absolutely. Anyone who's working on operating system development, concurrent programming, they're dealing with semaphores all the time.
Like so.
It's core to what they do.
So for those folks, for our listeners who might be interested in digging a little deeper into this world, any tips on where they could start?
Well, there's some great resources online, obviously, but one book I always recommend is Modern Operating Systems by Andrew Tannenbaum. Yeah, it's really a classic. It goes into a lot more depth about semaphores and other concurrency control mechanisms.
Fantastic. I'll make sure we link to that in the show notes. Now, before we wrap up, any final thoughts, maybe some things our listeners could ponder on their own?
Well, we've talked a lot about the upsides of semaphores, and they really are fantastic tools, but like any tool, they're not perfect, and there are potential downsides to be aware of.
Oh, interesting. Like what?
Well, for example, their reliance on shared memory can actually introduce new challenges. Like there's this thing called deadlock that can happen.
Deadlock. What's that?
Basically, it's where you get these processes that end up stuck, waiting for each other to release resources. It's like a kind of digital gridlock. But that's a story for another deep dive.
Ooh, I like it. Deadlock. It's on the list. Well, I think we've successfully navigated the world of semaphores today, thanks to your expert guidance.
I'm happy to help.
Until next time, folks, keep those processes running smoothly. Okay, so today we're diving into something that sounds a little, well, dry monitors in computer science.
Uh-oh, am I in for a technical lecture?
Not at all. That's the cool part. This impacts us every day, even if we never code. We've got this text that gets into the nitty-gritty, but our goal is to make it, actually interesting.
I'm all for interesting. So, what's the big deal with these monitors?
Think of it like this. You're streaming a movie, working on a document, your computer's juggling tons of stuff, right?
And it just works, usually.
Exactly. And monitors are kind of the unsung heroes, making sure those programs don't crash and burn while fighting over your computer's resources. Our source starts by describing what happens without them. And yeah, not pretty.
Oh, I bet. Like, is my computer going to melt down without these monitors?
Not quite. But the text compares it to a busy intersection with no traffic lights, cars everywhere, total chaos.
Oh, I see. So like instead of cars, it's programs all needing the same stuff, like memory or processing power all at once.
Bingo. That's where monitors step in. They bring order to the madness. They're like the traffic signals, making sure everyone follows the rules.
Okay, so instead of crashing into each other, these monitors make sure everything takes turns.
You got it. The text actually defines them as high-level synchronization primitives to ensure only one program can access a shared resource at a time.
Synchronization primitive.
Yeah.
Kitschy. But okay, I get it, preventing digital fender benders, right?
Exactly. So we've got the traffic system, but then the text keeps mentioning semaphores. What are those? Like the stop signs.
Even more basic, think of them as the traffic lights within our intersection. Green light, the resource is free, go for it. Red light, it's in use, you gotta wait.
Okay, so like a program pulls up, checks the semaphore light, and if it's red,
it chills out until it gets the green. Those PNV operations in the source are basically just a program saying, hey, I need that, and then, okay, I'm done, you can use it now.
So it's not just a free-for-all. But what about those times when a program needs something specific before it can go? That's where those condition variables come in, right? Those were a bit confusing.
Yeah, they're a little more nuanced. Stick with the traffic analogy, though. Imagine different lanes for different destinations.
Okay, so instead of everyone piling up in one lane, there's some organization to it.
Exactly. Let's say a program needs data that's still being processed. It can't just grab it, it has to wait until it's ready. A condition variable is like that designated waiting area, so it's not constantly checking if the data is ready yet.
So instead of honking its horn, it's patiently waiting in its lane. And then those C.wait and C-signal things in the text make more sense.
Yeah.
It's like being waved ahead when it's your turn.
You got it. And all of this, the semaphores, the waiting, it's all overseen by the monitor, keeping our digital traffic flowing smoothly.
Amazing. And to think all this is happening without us even realizing it. But what happens when some programs need to, cut the line? We'll find out after a quick break. So we've got our digital traffic system all mapped out. But in the real world, sometimes you need to, bend the rules a little. Like, what about those times when a program's on a tight deadline? Do they just have to wait in line like everyone else?
That's where priority waits come in. They're like the express lane on our coding highway.
Okay, makes sense. But how does a program get a VIP pass?
Well, instead of flashing lights, they have different priority levels. Our source mentions this thing, C.wait P. That little p is like assigning a number. The higher the number, the more urgent it is. The monitor uses that to decide who gets woken up first when a resource frees up.
So even with all this waiting, it's not just first come, first served. The monitor's playing traffic cop on a whole other level. It's kind of mind-blowing when you think about all this happening behind the scenes every time we use our computers.
It really is, and it shows just how much thought goes into preventing those digital gridlocks. But all this talk about traffic lights and lanes, it makes you wonder, how is this actually built? Our source dives into some pretty intense code examples, and I gotta admit, I kind of skim those parts.
Yeah, that's where I start to feel like I need a computer science degree.
Yeah.
But for those of us who, just use computers, what's the key takeaway?
The good news is you don't need to understand all that code to appreciate how it works. Think of compilers and preprocessors as translators. They take these concepts we've been talking about, monitors, semaphores, the whole shebang, and turn them into a language the computer's hardware can actually understand.
Okay, so they're like the architects, taking our traffic analogy and turning it into blueprints.
Exactly. And while the actual translation process is super complex, the basic principles are the same. It's pretty cool how these simple concepts come together to manage all that complexity, don't you think?
Absolutely. But we've been talking about this perfectly synchronized system, and, well, we all know nothing's ever perfect. So what happens when something goes wrong in this well-oiled machine? We'll tackle that question when we get back. So we spent all this time talking about these monitors, these amazing traffic controllers inside our computers. But even the best traffic systems have their limits, right? What happens when there's, like, a digital fender bender?
Well, monitors are designed to be pretty bulletproof, but there are definitely situations where things can get a little, sticky.
Sticky how so? Give me an example.
Imagine a program grabs a resource, but then for whatever reason, it never lets go.
Okay, so like it's just sitting there blocking traffic. What happens then? Does everything just grind to a halt?
It can definitely cause some serious slowdowns, maybe even a crash if it's not dealt with quickly.
Yikes. So what could be done?
Luckily, operating systems are smarter than your average traffic cop. They've got ways of detecting these situations and stepping in to, clear the roadblock.
Like what kind of ways?
Well, it might try to force the program to release the resource, or if all else fails, it might even have to terminate it completely.
Wow, so it's like calling in a tow truck for that digital roadblock. Makes you realize how important it is to have those safeguards in place.
Absolutely. But you know what I find really interesting about all this? It's not just computers that struggle with these kinds of problems.
Oh, totally. This whole idea of managing shared resources, avoiding conflicts, it's everywhere.
Exactly. Think about air traffic control. You've got all these planes coming and going, and they need to do it without crashing into each other.
It's like they've got a giant monitor in the sky making sure everything stays organized.
Precisely. Or even something like a bank managing financial transactions. They need to make sure two people don't withdraw from the same account at the exact same time.
Otherwise, chaos. It's amazing how these same principles pop up in such different contexts.
It really is. And it kind of makes you wonder what other elegant solutions are hidden behind the scenes of things we take for granted every day.
Well, I don't know about you, but I'm certainly a lot more aware of all the invisible forces keeping our digital lives running smoothly.
Me too. It's funny how a little deep dive can change your perspective.
It really is. And on that note, we've reached the end of our journey into the world of monitors. We hope you've enjoyed this peek behind the digital curtain and maybe even gained a new appreciation for all the amazing complexity that goes into making our computers work. Until next time.
Okay, so you've sent us some really interesting notes about concurrency control mechanisms in computer science. And I have to say, this is a topic that's always fascinated me. It's like, how do computers actually manage to do multiple things at once without completely freaking out?
Yeah, it's a bit of a juggling act, isn't it? You have all these different processes vying for the same resources, and it's all about making sure they play nicely together.
Exactly. And one of the classic problems in this area is the readers and writers problem, which you've mentioned in your notes.
Oh, right, the library analogy.
Yes, it's such a great way to visualize it. Imagine you've got a busy library, you've got people who want to read books, and you've got people who need to, make changes to the books or add new information. How do you manage that without ending up with a chaotic mess?
Well, the key challenge is finding that balance, right? You want to allow multiple readers to access the information simultaneously.
Because, there's no harm in having multiple people reading the same book, right?
Exactly. But the moment someone needs to make a change, like a writer editing a book, you need exclusive access.
Otherwise, you'll have people reading garbled sentences, half-updated information. Chaos.
Precisely. So that's the core of the readers and writers problem. Figuring out how to allow concurrent reads while ensuring that writes happen atomically without anyone else messing with the data while it's being changed.
And this problem isn't just limited to physical libraries, right? We see this everywhere in the digital world.
Oh, absolutely. Think about a shared document, like something you're collaborating on with colleagues. Multiple people can view it simultaneously, but if everyone starts typing in the same paragraph at the same time...
They're going to have a real mess on your hands.
Exactly. And that's why concurrency control is so crucial. It's those mechanisms that prevent that kind of digital mayhem from happening.
So how do we actually solve this readers and writers problem? Because it seems like a bit of a catch-22. You want to allow access, but you also need to maintain order.
Right. And one of the big issues we need to avoid is something called starvation. Imagine a writer who's constantly being blocked because there are always readers lined up. Or, on the flip side, readers who can't get to the information because a writer has it locked down. It's all about fairness.
It's like being stuck in a digital waiting room, never getting your turn. So how do we prevent that? Well, a common approach is to implement a system with two main rules. First, if a writer is waiting, new readers can't just jump in. They have to wait their turn. This ensures the writer eventually gets access. And secondly, once a writer's waiting, they get priority. Any new readers have to go to the back of the line.
Ah, so it's like a priority queue system, ensuring everyone gets their fair share of access.
Exactly. And one way this is often implemented in practice is through a mechanism called a monitor.
A monitor. Okay, tell me more about this. What exactly is a monitor in this context?
So think of a monitor as a kind of code bouncer.
Okay, I like where this is going.
It stands guard over that shared resource, whether it's a database, a document, or whatever needs controlled access. And it uses tools like counters and condition variables to manage the flow.
So the counter is kind of like keeping track of who's in the club, right? How many readers, how many writers.
You got it. And then the condition variables are like signals. They tell processes when it's safe to enter or when they need to wait their turn.
It's like the monitor is running a very, very organized party, making sure everyone gets their turn to use the shared resource without causing a scene.
That's a great way to put it.
Yeah.
And you see this kind of system in action everywhere, from managing database access to handling those simultaneous edits in Google Docs. It's fascinating stuff.
Okay, so we've tackled the library, but your notes also mention a scenario that's a little more, well, philosophical.
Oh.
The dining philosopher's problem.
Ah, yes. A classic. It's a thought experiment, really, designed to illustrate the challenges of deadlock.
Deadlock. Okay, before we dive into that, paint me a picture. What's the setup for this philosophical feast?
All right, imagine a group of, say, 5 philosophers sitting around a circular table. Each philosopher has a big plate of spaghetti in front of them, right?
Okay, so far so good. I'm sensing a metaphor here.
Exactly. Now here's the catch. They only have 5 forks. 1 fork between each pair of philosophers.
Ah, I see where this is going. You need 2 forks to eat spaghetti gracefully.
Precisely. And that's where the problem arises. If all the philosophers get hungry at the same time and they each grab 1 fork, everything grinds to a halt.
Because they're all holding out for a second fork that's never going to come free.
Exactly. Each philosopher is stuck, waiting for their neighbor to finish eating, but of course nobody can because they're all in the same predicament. That's a deadlock.
So it's like a philosophical standoff, except instead of debating existentialism, they're just holding forks.
Pretty much. And it beautifully illustrates how resource contention can lead to these situations where nothing can proceed.
And this isn't just some abstract problem, right? This deadlock thing can happen in the real world, too.
Oh, absolutely. Think about traffic, for example. Imagine cars at a 4-way intersection, each one waiting for the others to move. If they all move at the same time, you get a crash. But if they all wait, you get a deadlock.
So how do we prevent this? I mean, how do we keep these philosophers, or cars for that matter, from getting stuck? What are some solutions?
Well, one way to handle it is to introduce a rule that philosophers have to pick up both forks simultaneously. If they can't get both, they put their fork down and try again later.
So no more hovering over your spaghetti, eyeing the last fork. You either commit or you wait your turn.
Exactly. It ensures that only one philosopher at a time has the resources to eat, preventing the deadlock.
That makes sense. Are there any other ways to solve this?
Another approach is a bit more unusual. Designate one philosopher as left-handed. They always pick up the left fork first, then the right.
Ah, so we're introducing a bit of asymmetry to break the pattern. I like it.
It's a bit of a hack, but it works. By ensuring that not everyone tries to grab the same resource in the same order, you can avoid that deadlock scenario.
Okay, those solutions make sense, but I have a feeling you're saving the best for last.
You're on to me. You see, there's a more elegant solution, one that leverages that concept we discussed earlier, the monitor.
Okay, I was hoping you'd say that. So how does a monitor help our hungry philosophers?
Well, in this case, the monitor is like having a maitre d' for our dinner party. It keeps track of which philosophers are thinking, which are hungry, and most importantly, which are currently eating.
So the monitor is managing the flow, making sure no one's grabbing forks out of turn.
Exactly. Only when both forks next to a philosopher are free can they transition from hungry to eating. And once they're done, the monitor ensures a smooth handover of the forks to the next hungry philosopher, preventing that deadlock.
It's like the monitor is whispering, all right, you've had your fill, be a good philosopher and pass the utensils along.
Precisely. It's elegant, efficient, and it ensures everyone gets their fair share without any philosophical fisticuffs over forks.
I love it. It's amazing how these concurrency control mechanisms, even though we don't see them, are working behind the scenes to keep things running smoothly.
Absolutely. But speaking of smooth operations, your notes also mention something called the elevator algorithm.
Oh, right. That one always intrigued me. It's not about philosophers, is it?
Not this time. We're shifting gears from sharing to optimization, specifically optimizing how computers access data on a hard drive.
Okay, so instead of philosophers and forks, we have data and elevators. How does that work?
Think of a hard drive like a tall building, and the read-write head, the part that reads and writes data, as an elevator. The elevator algorithm is all about minimizing how much that elevator has to move up and down, because each movement takes time.
So it's about efficiency, making sure the read-write head isn't bouncing back and forth across the hard drive like a ping pong ball.
You got it. The algorithm works by having the read-write head move in one direction, say from the outer tracks to the inner tracks, just like an elevator going up. As it moves, it picks up any requests along the way. Once it reaches the end, it reverses direction and picks up any pending requests on the way down.
So instead of going up and down for each individual request, it's more like making a single, efficient trip, just like a smart elevator.
Exactly. It minimizes those long, time-consuming jumps, making data access much faster.
That's really clever. And you know what's even more interesting? This principle isn't just limited to hard drives.
You're right. The elevator algorithm, though designed for disk scheduling, is a great example of a broader optimization principle. Think about ride-sharing apps, for example.
Oh, right. They use a similar logic to group passengers going in the same direction, minimizing detours and saving everyone time.
Exactly. Or even package delivery writing. Optimizing those routes to reduce unnecessary back and forth is based on the same underlying principle. It's fascinating to see how these concepts can be applied in so many different areas.
It really is. This whole deep dive has been eye-opening. We've gone from managing readers and writers in a library to preventing philosophical standoffs at the dinner table to optimizing hard drives with elevators.
It just goes to show these fundamental computer science concepts, they might seem abstract at first, but they underpin so much of how we design and interact with technology.
And they highlight the importance of thinking about how we manage resources, prevent conflicts, and optimize for efficiency, even, or perhaps especially, when those processes are hidden from view.
Exactly. It makes you appreciate the elegance and ingenuity that goes into building the systems we often take for granted.
It really does. Well, on that note, I think we've covered a lot of ground today. A big thank you to you for joining me on this deep dive into concurrency control mechanisms. Until next time.
Ever wonder how computers juggle a million things at once?
Yeah.
Like you're downloading a huge file, listening to music, and editing a document all at the same time.
Right.
And your computer doesn't just, melt.
Yeah.
It's wild. How do they keep everything straight?
Well, it all comes down to this concept in computer science. It's called a critical section.
Okay, critical section.
It's kind of like, imagine, those velvet rips they have in clubs?
To make the line.
Yeah, to make a line. They create this kind of exclusive area
Right.
where only one person or maybe a small group of people can be at a time.
Makes sense.
That's kind of what a critical section is, but for computer processes.
So instead of a bouncer, you've got, code making sure only one process gets access to a resource at a time.
Exactly. That's a great way to put it. And that's what we're diving into today. We're looking at a classic solution to this whole critical section problem. It's called Peterson's solution.
Peterson's solution, and what makes it so special?
Well, for one, it's surprisingly elegant. It manages this whole synchronization thing, but it does it without using some of the usual tools, like mutexes. It's kind of like
Like performing surgery with just, a butter knife.
That's a pretty vivid image.
Sorry.
But yeah, it's kind of like that. It gets the job done with minimal tools.
I like it. Elegant solutions.
And it's specifically designed to work with two processes.
Okay, so two processes, like two chefs trying to share the same kitchen.
Exactly. Each wants to use the same resources, but only one can at a time, or things get messy.
So how does Peterson's solution keep our chefs from, a culinary disaster?
So imagine each chef has a flag they can raise.
Okay, I can picture that.
This flag is how they signal, hey, I need to use this resource. And then there's this spotlight in the kitchen.
There's always a spotlight in the kitchen.
Always. And this spotlight represents a variable we'll call turn. It can only shine on one chef at a time.
So the flag is I'm ready, and the spotlight is you're up.
You got it. So each chef raises their flag to say, I want to use the resource. But then they do something interesting. They point the spotlight, that turn variable, at the other chef.
It's like saying after you, very polite chefs.
Exactly. It's all about being courteous in the shared kitchen space.
But someone's got to go first. How does Peterson's solution break this deadlock of politeness?
Well, that's where the clever bit comes in. That spotlight, that turn variable, can only point at one chef at a time.
Right, one spotlight.
So even if both chefs try to point it at each other, only one of those gestures will actually stick.
Because you can't have two values in a single variable at the same time.
Precisely. The chef the spotlight is on gets to go first. They get access to the critical section.
While the other chef waits patiently, I assume?
Exactly. They're in the waiting loop, politely watching the spotlight.
So that's how it ensures only one chef is using that resource at a time.
Exactly. It's all about that elegant interplay of flags and the turn variable.
And that's Peterson's solution in a nutshell. But how does this translate to actual code? We've got an excerpt in the show notes for this deep dive.
Yeah, let's take a look. It's surprisingly concise, actually.
Hit me with it.
So the first thing each process does is set its flag to true. That's them raising their hand saying, I'm ready to enter the critical section.
Got it. Raising the flag.
Then they set the turn variable to the other process's ID.
Pointing that spotlight.
And then comes a critical part, the waiting loop.
The waiting loop? What's going on in there?
This is where things get interesting. Inside the loop, each process is checking two conditions.
Okay, lay it on me.
First, They're looking at the other process's flag. Is it raised? Is the other chef also trying to get in?
Makes sense.
And second, they're checking that spotlight, that turn variable. Is it their turn yet?
So it's like double checking before barging into the kitchen. Is anyone else trying to use this? Is it my turn?
Exactly. Both of those conditions have to be met, the flag and the turn, for a process to finally enter the critical section.
It's so cool.
It is. And that combination is how Peterson's solution makes sure only one process is in that critical section at any given time.
So this whole dance of flags and spotlights, it's not just about preventing crashes.
Yeah. You're right, it's also about keeping things flowing.
Like making sure the kitchen doesn't just grind to a halt because one chef is waiting for the blender.
Exactly. Peterson's solution hits on two super important properties in concurrent programming: progress and bounded waiting.
Okay, big words. Break them down for me.
So progress, it basically means that if one process is stuck waiting, it won't block everyone else.
Makes sense.
Like if one chef is waiting for the oven, the other one can still be chopping veggies, right?
Okay, keep things moving.
Exactly. It makes sure the whole system doesn't just freeze up.
I like it. What about that other one? Bounded waiting.
Yeah. So bounded waiting, it means that no process is left hanging indefinitely.
No one's stuck waiting for the oven for, like, an hour.
Exactly. Peterson's solution guarantees that a process will get its turn to enter the critical section.
To use the blender, to grab the whisk, whatever.
Exactly. After, at most, one turn by the other process.
So it's like you're guaranteed to get your turn in the kitchen eventually.
Exactly. It ensures fairness. No process gets starved out.
So Peterson's solution, pretty foolproof then, right?
Yeah.
Elegant, efficient.
Well, in theory, yes. But there's a catch.
Oh, there's always a catch, isn't there?
It's more like a quirk of modern computers. You see, they're obsessed with speed.
Okay, by tracks.
And to squeeze out every bit of performance, they sometimes rearrange the steps in our programs.
They do what? But we wrote the code in a specific order for a reason, right?
You'd think so, wouldn't you? But computers, they have their own ideas.
So we're talking about instruction reordering. I knew that was going to come back to bite us.
It's a bit like, imagine following a recipe, but the chef decides to, add the milk before the flour.
That's just wrong.
Sometimes it works out fine, sometimes you end up with a mess.
Okay, I'm starting to see where you're going with this. How does this reordering mess with Peterson's solution? Those flags and spotlights.
Imagine this. A process sets its flag to, it's ready to enter the critical section, right?
Right, raising the flag.
But before it can set the turn variable, point the spotlight, the processor swoops in and decides, nope, I'm going to do this other thing first.
So it's like the chef throwing in a pinch of salt when they should be adding the eggs.
Precisely. And suddenly, the other process sees that raised flag, but doesn't see the spotlight pointing the other way.
Because the processor got ahead of itself.
Exactly. And it thinks, oh, it's my turn, and waltzes right into the critical section.
Even though the first process was technically there first.
Exactly. Instruction reordering can completely undermine the whole system.
So much for our polite chefs.
And that's the problem. The processor, in trying to be helpful, introduces a critical flaw.
So Peterson's solution, it's great in theory, but
the real world, especially the world inside a modern CPU, well, it's rarely that simple.
So Peterson's solution, it's like great choreography, but our dancers are a little too unpredictable.
Yeah, it's a good analogy. In a perfect world, it works like a charm. But in the real world, those CPU gremlins and their reordering shenanigans,
They throw a wrench in the works.
big time. And that's why we have other tools, more robust tools for actual concurrent programming.
Right, like those mutexes you mentioned earlier.
Exactly. Mutexes, semaphores, they're like the heavy-duty traffic signals of the concurrent world.
Okay, so we've moved on from polite chefs to needing a whole traffic system.
Basically, when you've got lots of processes all vying for the same resources, you need a way to keep things flowing smoothly.
No digital gridlock.
Exactly. And these tools, they're designed with those hardware quirks in mind.
So they factor in those CPU gremlins?
Exactly. They're like, okay, we know you might try to reorder things, but we've got this handled.
That's reassuring.
Right. They act as a kind of contract between your code and the hardware, ensuring those critical sections stay protected no matter what.
So it's like no matter how much those CPU gremlins try to mess things up, the mutex is there to keep everything running smoothly.
You got it. It's all about guarantees. With Peterson's solution, there's always a chance, however small, that those reorderings could cause problems. Mutexes and semaphores, they take that uncertainty out of the equation.
So even though Peterson's solution might not be the go-to tool for everyday coding, it's still a really valuable lesson, right?
Absolutely. It shows us how even simple solutions can be insightful.
And it highlights just how complex this whole concurrency thing gets.
Definitely. Peterson's solution, it's like a stepping stone. It helps us understand the core challenges and then appreciate those more sophisticated solutions even more.
Because we've seen firsthand what can go wrong.
Exactly. It's like you can appreciate a really well-built bridge a lot more after you've tried to cross a wobbly one, right?
Makes sense. So for those of you who are ready to cross that bridge and dive deeper into mutexes, semaphores, and the wild world of concurrency, be sure to check out the show notes. We've got links to all sorts of resources to help you on your journey.
And remember, even though those low-level details might seem a bit intimidating at first, they're worth understanding. It's like knowing how the engine of your car works, even if you're not a mechanic yourself.
It makes you a more informed driver, and in this case, a better programmer.
Exactly. So buckle up and get ready to explore the fascinating world of concurrent programming.
And as always, thanks for joining us on this deep dive. We'll catch you next time.